So welcome back, everyone, and thank you for joining us today for this new webinar, Verifying the Hierarchical Structure and Freedom from Interference of Software Components. As usual, this is Lavinia, your host, and our speaker is Roberto Bagnara, who is a chief scientist at BUGSENG, other than a member of the MISRA-C and the WG14 working groups. BUGSENG is the designer of the ECLAIR static analysis platform, which allows almost complete automation of the checks for MISRA compliance. Of course, many of you are from the automotive sector today, so you'd be interested to know that ECLAIR is also qualifiable for ISO 26262, as well as for all other main functional safety standards. Only a last note before we start, please write your questions in the Q&A section, perhaps throughout the entire webinar. So at the end, we can reply straight away. All right, then let's turn this over to Roberto.
Okay, thanks for the nice introduction. Let's start. Here is the plan for the presentation. Even though there are many people from the automotive sector, there are also many people that are not from the automotive sector. So I will start with system decomposition by static analysis in a way that is completely independent from any safety consideration and any functional safety standard. Then I will bring safety into the picture to show how the same functionality that is able to check the interaction between software components can be used to enforce safety constraints. And then I will introduce ISO 26262 into the picture, trying to introduce the concepts I will be using. And then I will present this new product, which is the ECLAIR Project Organization Checker. And in the end, I will draw some conclusion. Okay, so managing complexity by decomposition. This is the first part. As everybody knows, a key thing about managing the complexity of software systems that are either large or critical or both requires decomposition. Decomposition means simply that you divide the system, the software components, into parts that are small enough to be reasoned upon, maintained, and tested in isolation first of integrating them into the wider system. So plain decomposition is nice per se. It allows organizing the program text. It's much better to have several small files instead of one giant file. It allows separate compilation. It allows to decrease some metrics about program complexity, but per se, just decomposition is not a big deal. So the real point is controlling the interactions between the parts. So the real advantage is when you keep the interaction under strict control. Okay, think about the components of a system as represented with a graph and the connection. So if any component may interact with any other component, then the complexity of the interaction grows quadratically with the number of components, as everybody knows. So this is a sort of spaghetti code, okay? So you should be very careful about this because spaghetti code is something that may destroy your project. So there are two flavors. Control flow spaghetti code. To do it really the professional way, you would need an unrestricted use of gotos. But even if every function may call any function, you can end up in quite a mess. And also there is the data flow spaghetti variant, in which you have many non-local variables and basically you have no policy for access. So every function may read or write any variable. So controlling interaction is the key. There are two concepts that are used in software engineering that are related with this. One is cohesion. Cohesion measures the dependency among the parts of a component. So when you have high cohesion, the parts in a component cooperate to the same task and they are strongly related. When you have low cohesion instead, The component seems to be just a container for unrelated parts. So you have put things in the same component for no good reason. Okay. The other measure is coupling. Coupling measures dependency among components. So when you have high coupling, it means that changing one component can likely have a high impact on other components. So high coupling is not a good thing, as you can guess. And low coupling means that changing one component does not affect or only affects marginally other components. Okay, so effective software decomposition strategies aim at breaking down programs into components so as to minimize dependencies among components, so low coupling, and maximize cohesiveness of each component, so high cohesion. There are well-known examples of strategies and paradigms to decompose software: procedural, algorithmic decomposition, or abstract data types, object-oriented decomposition. These strategies are orthogonal to the programming model. So linguistic support helps, for example, for object orientation, but it's not essential. You can develop an object-oriented decomposition even if you are not using an object-oriented language. Okay, so the criteria for decomposing systems are out of scope for the presentation. However, there are a few that are so well known that it's nice to recall them. So one is layering. It was introduced by Dijkstra in 1968, and he put it that way: any system should be designed and built as a hierarchy of layers, where each layer uses only the services offered by the lower layers. Another possibility is orthogonal. It's vertically dividing a system into several independent or weakly coupled components. This is usually called partitioning. Another strategy is called information hiding. This was introduced by Parnas in 1972, and the philosophy was hide all what is likely to change. There are more, of course. Okay. So, and in addition, several criteria are often used at the same time. For example, combining partitions and layers is very common. So the main difference is this: while partitions are divisions at the same level of abstraction, a layer is a component that provides services at a given level of abstraction, and it depends only on lower layers, and it has no knowledge of higher layers. There are variants, of course, in the software engineering literature. For example, we talk about opaque layering, when a layer may only refer to the layer immediately below, and this is the right thing to do when your main design goals are maintainability and flexibility. And there is also the less restrictive option of transparent layering, when a layer may refer to any layer below it. And you may want to choose this when one of your important design goals is runtime efficiency. Okay, so proper decomposition, meaning low coupling and high cohesion, is important for several reasons, and some of which apply to all kinds of systems. Notice that I didn't mention safety or security yet. It's good anyway. So the advantages are well known. It's systems that are properly decomposed are easier to design and to develop. It's easier to do component verification. System integration and verification is easier, and maintenance is easier. And of course, when safety and security come into the picture, things are even more interesting. And in any case, unwanted or unknown dependencies or interference among components easily turn into safety and or security issues. Okay, this is the key thing to understand. Let us start with a simple example that everybody knows. So it's the open system interconnect model for network applications. So everybody knows there are 7 layers. So in the complete picture, we have the application layer, presentation layer, session, transport, network, data link, and the physical layer. And this is the structure of the so-called OSI model. Okay, so there are several reasons why this is a good idea. And in the small presentation I give now, which contains also a little bit of practical demonstration, we will ask the question, how do you check system decomposition? Now, suppose you have designed your system following the OSI model. So how do you check that the implementation complies to this aspect of the design? Of course, the answer, one possible answer is you check by hand. So but everybody can easily guess that this is time-consuming, it's error-prone, and everything should be multiplied by the number of times you need to redo the check. And if you think to solve this issue by doing the check only at the end of the project, then you are risking, okay, especially if you have to follow the architecture. So you may discover at a late stage in the project that there is some interaction that is unwanted, and making changes to the project at the end may be very expensive. And the other possibility, which is of course the one that we advocate, is by doing the check by static analysis. You need some little time to encode the decomposition into a tool configuration, but then the check is completely automatic and reliable, and it can be part of your continuous integration processes. So you can keep these interactions under strict check every day. Okay, so let's try this simplified OSI model. So suppose we have an application software program that needs to use the services of a network stack, a simplified network stack. Let's suppose the network stack has just the three software layers identified by data link, network, and transport. And we want to make sure that network layers are not bypassed. So, for example, because this is bad per se. For example, if the data link component is accessed bypassing the network component, then there is a possibility that we will build a packet that cannot be routed because the network component didn't have a chance of adding the information required for routing. Okay, and in order to make the example a bit more interesting, we want to allow for an exception. The application component may call a particular function in data link, which is called link status, which is a Boolean that may be true if the sorry, it's not a Boolean. It's a enumeration, as we'll see, that may be good or bad. The link is up or down. Okay, so let me show you a little bit of the sources of this small program. I hope the screen is readable. Here we have the main program, which is in the application layer. It is including the transport layer header files and also the data link layer header file, because we have said that the application layer must be able to check the link status. So the program says if the link status is different from good, then we print an error and exit. Otherwise, we use the transport layer send packet function to send hello world. And if something goes wrong, then we print an error and exit. And then there are two things that I've put here that shouldn't be done. So it should be forbidden. In this in function invocation, the data link send packet function is being called bypassing both the transport layer and the network layer. So this is illegal. Okay, and also here a variable which belongs to the data link layer, which is a counter counting the number of bytes that have been sent is also accessed, and this is not part of our configuration. So this also should be a violation. Okay, let us have a look to the data link layer. Okay, so this is the counter counting the number of bytes that have been sent. This is the packet sent of the data link layer. So it's mostly MISRA compliant code. It does all the checks that have to be done to make sure that there is no buffer overflow. It adds the data link header data to the packet. It computes a CRC and it adds the CRC at the end. Okay, and then it sends the packet. Okay, and then it increments the number of bytes that are sent, and there is some little checking that what we have sent is the entire packet, and we didn't fail to send part of it. Okay, so this let me go on with the presentation. I want to present now the configuration of the tool. Okay, so the first part of this configuration, it says that we only consider, for this example, variables and functions with external linkage in user code, so not system code. Okay, so the set of all component entities are made of all entities that have external linkage, so we disregard internal linkage entities, that are of kind variable or functions, and such that all their declarations are either in the main file that is compiling or in a user header file, not system header files. Okay. Then we want to associate program entities to components. We have said that the link status function is an exception because we want the application layer to be able to directly access the data link component, but just to call this link status function. So here we say that the function that is called link status, here we are in C and not C++, so we need not specify the types of the argument, as we don't have function overloading. In C++, it would be we would have this possibility, of course. And we put this in the exceptional area of the data link component. Then everything else that is declared in the dl.h header file goes into data link. Similarly, for the network and the transport layer, they all have another file, this for convenience. So there are other ways of putting program entities into components, but if you follow a certain discipline, which by the way is also recommended by MISRA, it will be very easy to define if you have a correspondence between header files and the layers to do this. And then finally, the main function is in the application layer. Okay. Then we have, this is for the program entities. As I will say again, with this tool, we can check dynamic dependencies, so runtime dependencies, function calls, access to memory, read and write to variables, and we can also check static compile time dependencies. So in order to do both these things, we also want to associate files with components, because then we want to be able to say, hey, you are not assumed to include this header file, because this header file belongs to a component to which you are not supposed to have access. So this is very easy. So we associate the source files to the components. And then we have to define the permissions we give to the components to interact between themselves. Here we are, this example is based on the OSI model, which is a layering structure. So it is very easy in this case to define the permissions in terms of a relation. So we define a relation which is called over, meaning directly above in the OSI model. Over is just a keyword, so it could have been any identifier. We are defining the relation called over, and we are saying application is over transport, transport is over network, network is over data link. Okay, and then with the help of this relation, we can define permissions. So component allows is saying this first directive says that the access is allowed if the two components are in the relation we have just defined over, and if the action is either include or call. So include for static dependencies, inclusion of header files, and call is an action that has to do with functions. Okay. And here is our exception. So the application layer, as an exception, can access the exceptional area of data link for actions include and call. Okay. So now a small demo. It will be very, very quick. This is the graphical user interface of ECLAIR. So this project has a name. The environment is very small. There are just two things in the path that allow me to invoke the compiler. Here I have to say which compilers should ECLAIR intercept, because as you may know, ECLAIR works by intercepting the toolchain, so intercepting any compiler, linker, assembler, librarian invocation, and obtaining automatically from the toolchain all the information that are required to perform a correct analysis. Services, I am just enabling this project organization checker service of ECLAIR. I'm not treating any file specially. I have a build task to compile the system. So let me show it to you. It's here. So it's build.sh. I'm simply compiling everything. Okay, data link.c, network link.c, transport, data link layer, network layer, transport layer, and the main program. Okay, I can build it like this. Okay, I have obtained an executable, an executable file that I can execute. And here it is. Of course, this is just an example. You can see the data link header, the information added by the network layer, the information added by the transport layer, and then hello world, and then the CRC. And then we have also the two forbidden functions. They are forbidden. They are not forbidden at the C level. They are perfectly legal. You can see that here we have built a packet that misses the network header structure. So this is a packet that cannot be routed, of course. Okay. Okay. So settings. This proj.org.ecl is just the configuration you have seen in the slides. So it's this file without the comments. It's just what you have seen in the slides. Okay, so I just ran the analysis. Okay, the analysis is finished. I can now view the results. Okay, and you see that I have two violations, and two violations in the project organization checker. So let us look at these violations. First violation, there is a call action from the application component to the data link component. Where it is? Okay, you see that I go here. Okay, now I can see what is the call action that is in violation of the project organization constraints. Okay, and here I see an explanation. So this is in data link component. this, the main function, is the application component, so this is illegal. Okay. The other violation, we have a read action, okay, and we are reading a variable which is in the data link component, and the function that performs the read is in the application component. So this is another violation. Okay, this is just to give you a rough idea of how it looks like on a very, very, very simple example. Okay, so let's bring safety into the picture, even though most of you should already have guessed that basically safety and security are not different. So it simply means that you will pay attention to a certain kind of interactions for different reasons, okay, for additional reasons. Okay, so let's start with something that is not related to ISO 26262. It's a very coarse safety specification with just two components. One is called SR, shorthand for safety related, and the other one is NSR, shorthand for not safety related. Okay. In this example, we only look at functions and function calls. We don't look at variables in this example. Okay, and since SR and NSR may not constitute a partition of the system, so we may have functions that are neither in SR or in NSR because we have made a mistake. For example, our classification of function is incomplete. We also use in a component called unknown. Okay, so here I notice now that I have double quotes that are unnecessary here. Anyway, so in the safety related component, I put function that whose name is fun1, fun2, and not safety related, I put all the functions that are in the not safety related component. And now, what is the safety constraint in this very simple example? The safety constraint is that the function in SR may only call other function in SR. What is the rationale? Of course, if the function f is safety related, it means that it has to be developed and tested according to stringent standards, okay, because it's safety related. And if f calls g, then also g must be developed and tested according to some standard. So roughly speaking, a reliable function cannot call a non-reliable one, for otherwise neither would be reliable. Okay. Okay. So by default, calls are always allowed between functions in the same component. So SR may call function in SR. We only need to specify that calls from NSR to SR and unknown are okay. Okay. Not safety related function may of course call not safety related function, but they can call also safety related function or unknown functions in this example. This is the first line. Okay. And basically we put no constraints on unknown functions. So unknown functions can call safety related function or not safety related function. And all calls that are not explicitly allowed are reported as violations in the same way I have shown before. Okay, so there's a message from the tool saying, hey, here you are doing something that is not in the, does not respect the constraints you specified for the project organization. So let us bring ISO 26262 into the picture. So I've tried to be very so basic so that everybody can follow. So in ISO 26262, there are several concepts that we need. One is the concept of cascading failure. A cascading failure is a failure that causes an element to fail, which in turn causes a failure in another element. So the picture here is this domino, where if something falls down, then what it's near to hit falls down as well. So this is a cascading failure. Whereas a common cause failure is the failure of two or more elements resulting directly from a single specific event. And this is called the root cause. Here is an example the root cause is lack of RAM, and this causes two failures at the same time. One is that the phone freezes, and the other is that text messaging doesn't work any longer. Okay, so this is an example of common cause failure. And a dependent failure in ISO 26262 is either a cascading failure or a common cause failure and nothing else. So the set of dependent failures is the union of cascading failures and common cause failures. So in other words, dependent failures are dependent if they are not statistically independent. So that the probability that both of them occur is different from the product of the probabilities that one and the other occur. Okay, so they are dependent. They may be a positive dependence. For example, failure A may make failure B more likely, so it's a positive dependence, or failure A may make failure B less likely, so this is a negative dependence. Okay. Okay, so now I have to define what is freedom from interference. Freedom from interference is the term which is explicitly defined in ISO 26262 is as the absence of cascading failure between two or more elements that could lead to the violation of a safety requirement. Okay, so only cascading failures are matter for freedom from interference, whereas independence is the absence of dependent failures between two or more elements that could lead to the violation of a safety requirement. So since cascading failures are a subset of dependent failures, achieving freedom for interference is instrumental in achieving independence. So please, one important thing is that I didn't mention automotive safety integrity levels yet. So why didn't I do so? Because freedom from interference and independence are two concepts that do not depend on ASIL. The ASIL come into play when considering the applications of this concept in ISO 26262. Okay, so when do we have to achieve independence or freedom from interference between the software architectural elements? There are three cases. So first case is when we are using ASIL decomposition, which is a way of lowering the cost in some cases. So it is when independent elements with lower ASIL are used to implement an element that has a higher ASIL. Okay, so it is crucial, of course, that these multiple elements are independent. Otherwise, there is no rationale for implementing with those a safety goal with a higher ASIL. Okay. The second case is the implementation of software safety requirements. For example, if we, as a software, as a safety mechanism, we may use a monitor. So a monitor is monitoring a monitored element. However, they must be independent of, because otherwise, of course, there is no gain. So there is no improvement of safety if the monitor and the monitored element are dependent from one another. Okay. And the third possibility is when we require coexistence of software architectural elements. So, for example, when we have functions implementing different architectural elements within the same program, and of course, we must make sure they do not interfere with each other in a way that is relevant for safety. So let us focus on this third point. Okay, so there are criteria in ISO 26262 to tell you when you may have elements coexistence. When the first is obvious, so if you have multiple coexisting subelements, you may, of course, develop them in accordance to the highest ASIL applicable to the subelement. So if you are putting in the same program functions that have ASIL, the most critical ASIL, and function with the lower ASIL, you can, of course, develop everything according to the prescriptions applicable to the highest ASIL, but this is expensive because developing to more stringent standards is, of course, more expensive. And the other possibility is absence of interference between the subelements. You have to demonstrate this. And in essence, what is absence of interference? It's basically a lower ASIL failure cannot cause an higher ASIL failure in the coexisting elements. Okay, so there are no cascading failures from a sub-element with no ASIL, so quality management, or a lower ASIL to a sub-element with a higher ASIL, such that this cascading failure leads to the violation of a safety requirement of the element. So in a sense, absence of interference is a weak form of freedom from interference. So freedom from interference means no cascading failures that can impact the safety. In absence of interference, it is less. Okay, so it's okay if an high ASIL component causes the failure of a low ASIL component. It's not the other way around, of course. Okay, so in ISO 26262, you have to, when you have to prove independence or freedom from interference, you have to perform what is called a dependent failure analysis. Okay, in these three cases I have said, so ASIL decomposition, implementation of software safety requirements, or required coexisting of the software architectural elements. So dependent failure analysis, if you need freedom from interference, as in case 3, you need to study all potential cascading failures. If you need independence, then you have to do the same, plus you have to investigate the common cause failures. And the algorithm, more or less, is this one. If you have to prove independence between two elements, A and B, right? Okay. So you have to examine all the potential cascading failure. So until you have examined all of them, so if there is a safety goal violation, then you can examine the next one. If there is a safety goal violation, A and B are not independent. Once you have done all, you have examined all the cascading failures, you start with common cause failures. Those that are that do not involve the violation of the safety goal are fine. And as soon as you find one, they are not independent. And if you exit this way, then you have provided evidence for independence. Okay. So let us focus on freedom from interference. There are several ways in which components may interfere in this sense. Timing and execution. Okay, so one may, for example, delay the other or block the other. They can interfere via memory or via the exchanges of information. So in ISO 26262 for ASIL-D, software partitioning must be supported by dedicated hardware features. For example, memory protection units. Memory protection units can be used for this purpose. However, this can only enforce partitioning of memory areas and system-on-chip peripherals. So for you need something else in order to ensure freedom of interference. So it's, of course, a must having an MPU, but it's not sufficient. Okay, so let me now introduce ECLAIR project organization checker. So why is this relevant? It is relevant to do part of this work, to facilitate you doing this kind of work by keeping under strict control the interactions. Actually, not only this. So the first way in which ECLAIR can help is due to support of the MISRA guidelines. So the MISRA guidelines have something to do with this, because applying them reduces the risk of execution blocking due to unexpected excessive loop. Okay, so for example, to make sure you don't have loops that take too long, you will in MISRA compliant code, reasoning on loops is much easier due to the restricted form they can take. So this is something in the timing and execution category. You can also, by complying to the MISRA guideline, you can prevent stack overflow, which is in the memory category we have seen. And plus, of course, the ECLAIR project organization checker, which is something that I have quickly demonstrated a few minutes ago. So, as I said, with the ECLAIR project organization checker, you can check dynamic runtime dependencies by tracking function and method calls. You can check pointer variables. The actions you can control are read or write access to the pointee. Okay, for any other variable, including pointer variables, the actions you can check are also read or write to the variable itself. Structure fields, you can treat them like variables, so you can check read or write access to those. And of course, you can check static compile time dependency, tracking files. The actions you may control is inclusion. So can this include this other file? And also macros. And the actions you can control are the expansion action, and you can also have finer control on the macro after expansion. And this is necessary, for example, when you want to work with the header files provided by hardware suppliers. So they are usually very big. That it's all in there. There are a lot of macros that are defined. Some of them are very critical, and because, for example, they contain addresses of very critical parts of the systems. Other are less critical. Okay. There are macros, for example, to enable interrupts or to disable interrupts that you may want to keep under strict control. And maybe other macros which are perfectly fine to be used. Okay, so this is why it is important to check dynamic dependencies and also static dependencies. So the ECLAIR project organization checker is available starting from ECLAIR 3.9.0, which will be released this Friday, so in a few days. And it is available with all ECLAIR packages, including B, which is our entry-level package. So it comes with all the advantages of the ECLAIR software verification platform. Some of them I've already mentioned. So most importantly, there is no need to care about the implementation defined aspect of the tool chain. They are all ended automatically, particular, predefined macros. Predefined macros that are influenced by the compiler options you are using. So they are all ended automatically. So you have a guarantee that you are actually analyzing what is compiled. Okay? There is a sophisticated reporting technology. You have seen, I have been using these interactive detailed reports with the full details about the preprocessing phase. You have seen that I was hovering over sections of the reports and preview windows were opening. There are many other interesting features that I have demonstrated in other webinars, and you can find them in our YouTube channel. You can also generate summary reports that are ideal for printing in OpenOffice, Word, or PDF. And you can have pure text qualifiable reports. So another feature of the ECLAIR software verification platform is powerful integration with most popular IDEs and with Jenkins. So I mentioned continuous integration and the importance of keeping the interactions between the project components under check continuously, and Jenkins is one ideal way to do this. And of course, everything is qualifiable in two ways. You can buy qualification kits, or you can buy qualification service where we do almost all the work for you. So, conclusion. We illustrated the importance of constraining the way software components interact. It is, of course, something that is told in very first courses about software engineering. So we have started describing this in purely software engineering terms, so why it is good anyway to limit interaction. And then we have introduced gently, I hope, safety and security into the picture. So we gave a brief introduction, which is of course incomplete, to the notion of dependence, freedom from interference, and absence of interference in ISO 26262. One complication some of you may have noticed is that freedom from interference is not the same thing as absence of interference. There is a subtle difference between the two concepts. And we have shown how the ability to control the interaction by static analysis is instrumental in gathering the evidence you need to prove independence and freedom from interference and absence of interference in a reliable and completely automatic way. So I've mentioned the availability of this new ECLAIR project organization checker that allows to configure and automatically check all sorts of constraints. So the examples I've shown are very simple for very simple systems that are partitioned in a very simple way, but the system is much more flexible in order to be able to capture all software decompositions strategies you may want to use. Okay, so last thing I want to mention, for those of you in the automotive sector, this is another important addition to ECLAIR support for ISO 26262. Anyway, most of the things I said are very relevant also for other functional safety standards in which you have to control the interaction between components, and you have to provide evidence that bad things don't happen. Okay, so I said basically all I wanted to say. If you have questions, I will be happy to try answering them.
Thank you, Roberto. Before we dive into the Q&A section, since you mentioned this several times, let me just point out that we wrote a brochure listing the several objectives of ISO 26262 addressed by ECLAIR. Of course, you can check it out in the Q&A section, but we'll provide it in the post-webinar mailing as well. All right, so let's now move on to questions. So you have demonstrated how to specify and verify separation of function calls between components. That looks nice, thank you. Can you do something similar for data passed between components?
Yes, as I've shown in the example, we can track read, write accesses to objects in other components. And also, as argument passing implies function call, the answer is yes. So the checker can track that. I have shown a small example where a variable in the data link layer was illegally accessed by the application component.
Second question, is there support available to install and deploy ECLAIR in the company's tool chain? What about customization and adaptation to the existing software development process?
Well, there are other webinars in our YouTube channel that you can check, but of course, ECLAIR has seamless integration with basically everything, every development process. So, as I shown, well, I didn't show this, but basically, ECLAIR works by performing the build. So the usual build you do, any way you build the the project. So in my case, it was a simple script, build.sh, that builds the system. Well, the graphical user interface under the hood simply executes this build.sh script in an ECLAIR environment. So it is the build task. So here we say to ECLAIR, in order to build the project, you change to this directory, which is the top-level directory defined in the project part of the graphical user interface. And then you run the script build.sh. And this could have been make or Ant, Maven, or Ninja, or really any other thing. So ECLAIR doesn't care. ECLAIR simply intercepts at a very low level in the operating system all invocations to the compiler, the linker, the librarian. So here is. So anything I list here, I can list more compilers here if I want. Linkers, assembler, librarian, they are all intercepted. And ECLAIR contains a very precise model of each of those in order to, among other things, capture the dependency these tools have on their command line options.
Thank you. So how can one check the project organization, for example, layer constraints, if the function pointers are used?
Okay, so if a function pointer escapes from a component, so it is passed, it is stored, then it is considered as a possible call, so possible invocation. So in this case, the checker will say caution. Okay, there is a potential for a violation here.
Is this project organization checker a product that is sold separately?
No, we have decided to include this project organization checker in all the ECLAIR packages, starting from the entry-level one, which is called B, and also, of course, in the MISRA packages to check for MISRA C, MISRA C++, and so on.
Is this new ECLAIR tool suitable for larger projects or as well as small projects?
Yes, it is. Of course, it is a new tool. We have made tests with the Linux kernel. So we have taken the Linux kernel, taken a definition of safety-related and non-safety-related function, and the results were pretty good, both in terms of performance and, of course, precision. The precision, I mean, due to the technology we use for the checking, so in which we use exact parsing, not approximate parsing, the tool is exact in this sense.
Okay, and that was the last question. Thank you, Roberta, but especially thanks to all of you for being with us today. Of course, if you have more questions, please write to info@bugseng.com. And same if you'd like to know our take on your projects, or more specifically, if you need to comply with MISRA, or even qualify your project with ECLAIR, the BUGSENG team will be more than happy to guide you through it and provide you with highly specialized training, consulting, and qualification services. Here is where I usually remind you of next webinar, but we actually haven't scheduled one yet, sorry. We are, as you saw, working on a few new gems, and all I can say at this stage is that we will introduce them in a webinar. We're not sure yet if in mid-December or right after the holidays, the beginning of January, but we'll keep you posted anyway. In general, a good way to know what we're up to is following us on LinkedIn and subscribe to our monthly blog. Of course, we'll send you the links in the post-webinar mailings. All right, and that was it from us today. So thanks again, and we hope to hear from you very soon and see you all next time. Have a nice day, everybody. Bye-bye.
Bye-bye.